Hi folks, and welcome today to Lesson 8.2. This is our second day talking about hypothesis tests for the population proportion. Yesterday we had some experience doing those tests. Today we're going to talk about some other issues that are involved with hypothesis tests. Some of you will be very happy to know that your TI 83 or 84 can perform a hypothesis test for the population proportion. I want to write the keystrokes for that here, and I'll show you what I'm talking about. The way to get here is stat and test. And actually, I guess I should show you stat and down to tests. There are a variety of tests and intervals that can be generated here, and I didn't show you the confidence interval before because I wanted you to do it by hand before we saw this. However, your calculator can do a confidence interval, and if you wanted the confidence interval, that is the one prop z int, and now I see tests, but we haven't found an interval yet, so I'm going to just scroll through here. There's an interval. We want the one prop z int. There it is. That will give us a confidence interval. That's choice A. It'll give us a confidence interval based on a sample proportion. Today we're talking though about hypothesis tests, and we are looking at a hypothesis test for a single proportion, and that would be this, a one prop z test, and one proportion z test. That is option 5. And we're going to probably lean on this a little bit today because we want to get beyond the set up the test and find the statistic. We want to be able to do a little bit more with it. The calculator can do the test for you for sure. However, you're the one who needs to interpret the results. And to do that, folks, we're going to remind you about the p-value. Okay? The p-value is the lowest value. So we said yesterday that it's the probability that another statistic would be as extreme as yours, and that is true. Another way to phrase that is the p-value is the lowest level of significance where you would reject. Lowest level of significance for which you'd reject. So, if you're going to do this kind of interpretation, you must use this kind of thinking. Compare the p-value to alpha, and we did this in yesterday's notes. Compare the p-value to alpha, ... If the p-value is less than alpha, you reject. I don't know, I heard this little rhyme. I think it's in your textbook. This always helps me to remember it though. If the p is low, the null must go. So if p is low, they probably should make it not quite so poetic and say if the p-value, but they say if p is low, the null must go. And you know, I like a little memory gimmick every once in a while. This is a good one for me. Helps me to remember. So let's investigate this a little bit. We have a situation. We're going to take a look at this little example. Jenny must have some time on her hands. She wonders if when you spin a penny, that is, set it up on its edge and flick it so that it spins around, she wonders if heads and tails are both equally likely, or if the probability that when you spin you'll get a head 50% of the time. She asked the question, should she reject the standard that is true, testing at the 05 level? I'm going to ask you to take just a couple of seconds and check those, the 3 criteria you need are p hat and q hat are sufficiently large. That is, p hat is 14 out of 40, q hat is the other 26 out of 40. When you multiply both of those by 40, you get 14 and 26, so the sample size is okay. N times p hat and n times q hat are both larger than 10. The size of the population is infinite because you can spin pennies as many times as you want. So our population is large enough. And this is a binomial situation. It either lands on its head or not. Okay, you must check those. Let's set up our null and alternate hypotheses. The null hypothesis is that the proportion of pennies that are spun and land on their heads is 0.5, or half the time. The alternate hypothesis for Jenny is that maybe not. It doesn't say that she thinks it's bigger or smaller, just that she's not sure that it's 0.5. You should state that in words. So the proportion of pennies, of spun pennies that land heads up is 50%. All right, we're going to let our calculator find the statistic for us. So I'm going to say z is equal to, and then I'm going to come to my calculator. We're doing a 1 proportion z-test. That's option 5. H sub o, P sub o, okay, the terminology a little bit different here, is 1/2 or 0.5. X is the number of successes that you got, 14 successes. And of course, number of trials, 40 in this case. We are testing a not equals to, so I'm going to go ahead and set that. And then I'm going to hit my calculate button. And here we go. Z is approximately, I guess I should put squiggles in here, -1.90. Now, you got Z from here. You can also check the p-value. Notice it here. P equals, this is your p-value, and that's about 0.06. Okay, now you are the one who has to make the judgment, folks. Your judgment should still include a picture. If we're testing at the 0.5 level, which is what she said, then we need to get beyond -1.96. We did not get beyond it. We got very, very close, -1.90. The p-value, 0.06, is not less than 0.05. We fail to reject H sub o. We didn't hit the shady part. And our p-value is not less than alpha. You'd finish the rest of the sentence, and I don't have the room here to do this. You'll notice, however, if we were testing at the 10% level, our p-value, which was 0.06, is less than 0.10. At the 10% level, we would reject. It's not that you have to figure Z again, it's just that you have to look at that p-value, which is what makes it such a great tool for making a determination, okay? At the 10% level, we'd reject H sub o. Suppose she tests the hypothesis that she got fewer heads than expected. That is, what if she changed her thing to a one-tailed test? So change H sub a to being the proportion is less than 0.5. If that were the case, and she was testing at the 0.5 level, the z-score for a one-tailed test at the low end is -1.645. And she definitely, with a z-score of -1.9, would be rejecting here. Okay? Let's do that test again, because things change, folks, when you change the null or the alternate hypothesis. So stat and down to tests, and we want the 1 prop z test. There it is. Our H sub o is the same. This is the same. What changes is our alternate hypothesis. And now we're testing a less than. So let's go ahead and hit enter here. This will change, folks, the p-value. It will not change the test statistic because z is z. It figures it the same way. We have a test statistic that comes out at negative 1.90. That's not changing. Okay? What does change is the p-value. In fact, if you look at this, the p-value is now 0.03. So not only would we reject at the 5% level, because remember, if the p is lower than alpha, 0.03 is less than 0.05, she'd reject. But you can be more strong than that. You can say she'd reject at any value of alpha that's greater than 0.03. Right? That's the p-value test. At the 1% level, so if we changed it to make a much more stringent test, she wouldn't get there. The critical Z for a one-tailed test at the 0.1 level is 2.33, and our statistic would not get there, but we could tell much more quickly by looking at the p-value. 0.03 is larger than 0.01. That means we fail to reject. All right, I'd like to get into a little philosophical discussion with you for just a moment about hypothesis testing. A hypothesis test does make decisions about what is correct and what is not correct, and it's basing it on the result of one sample. So you're really placing a lot of weight on a single sample. I'd like you to think about what could go wrong. This process is similar to a trial by jury, folks. The defendant is either innocent or guilty in a trial, and the jury is going to choose one of those things. The jury will say he is either innocent or guilty. And if you think about that for just a moment, it's way possible that a person can be innocent and yet be found guilty. They would have made a mistake, but that's a possibility. It's also possible that a person is guilty of the crime and is declared innocent. That is also a terrible mistake. Both of those things are bad. We don't want either of them to happen. So just in the same way, your hypothesis test, especially when you think about this in business, folks, I mean, people are making decisions about your safety. How much error is there allowed to be in the size of, I don't know, maybe bolts on airplane doors, right? You want them to have you want them to make safe decisions. And hypothesis tests are actually used to do those kinds of determinations. So I want us to think about this. Suppose the null hypothesis is actually true and we fail to reject it. It was true and we don't overturn it. That means that we've done the right thing. That's a correct choice. If the null hypothesis is actually false, however, and we fail to reject it, that's wrong. That's a wrong choice. They made the wrong decision. On the other hand, what if the null hypothesis is true and you decide to reject it? If it's true and you overturn it, you also have made a wrong decision. In the criminal case, this would be the person committed the crime and you don't sentence him. In our justice system, we're assumed to be innocent. So if the null hypothesis is that the person is innocent and we reject that, then we've imprisoned him wrongly, okay, or her. If the null hypothesis is actually false and you reject it, then you've done the right thing. You've made a good decision there. All right? A type 1 error happens when H sub O is true and you reject it. It's called a type 1 error. All right, H sub O is true and it's rejected. This is a type 1 error. I'm going to put a little 1 right there. The type 2 error is the other one. When H sub O is false, that is, it's not correct, but it's not rejected. So that makes this the type 2 error. H sub O is false, not rejected. Okay? Both of those situations have issues, and we need to talk just a tiny bit about them. Suppose that the null hypothesis is true. Okay, the only way that you can make a type 1 error would be to reject a true null hypothesis. You'd have to get an extreme value from your sample. It would have to be something very significant. If you're testing at the O5 level, there's always a 5% chance then that could happen by chance. I mean, 5% of the area could be hit by chance alone. So if you got an extreme event, then there's a 5% chance you're going to make that type 1 error just by chance. It doesn't matter what the sample size is. That's not going to help in this thing because there's always a 5% chance. To lower the chance of making a type 1 error, the statistician should decrease the level of significance. That is, if you don't want there to be so much wiggle room out here, then make alpha lower. Decrease the level of significance. That reduces your probability of making that type 1 error, rejecting a true H sub O. Okay? However, if you lower the level of significance, it makes it harder to reject H sub O if it's false, right? Lowering the level of significance moves this out this way, okay? There's less shady area to get into. If you do that, it's harder to reject H sub O, whether it's false or true, but particularly thinking about the type 2 error, if it's false, you don't want that either. So to lower the chance of making this kind of error, you either increase sample size and you'll recall that increasing sample size lowers standard deviation and it makes it harder to get out to the extreme values, or you increase the level of significance. That is, increase alpha. Of those two things, again, this is my opinion. You're always getting my opinion, but I would say this is the safer. If I want to lower my chance of making that type 2 error, I'm going to just ask more people. I'm going to increase my sample size because to me that is safer than messing around with the level of significance. I don't want to accept more risk. Okay, I want my test to give good results. Actually, the power of a test is the probability that H sub O gets rejected. Probability. The probability that H sub O is rejected. In our class, we're not going to ask you to figure that probability. That's for a higher level of stats than us. However, you should just have heard the term, the power of a test. It's the probability that H sub O is rejected. When H sub O is false, you want it to be rejected. Therefore, you want the power to be large. Okay? You want to reject when you're supposed to. So the power of a test, you want it to be large. All right, that brings us to the end of our discussion about hypothesis tests today. Please get out there and try that. You try at your earliest convenience.